Hi everybody, this is an example problem from lecture 12 on fluid statics. This is a supplemental example on solving a manometer problem, and I've taken the liberty of drawing the problem already since that takes me a long time sometimes in these examples. So what we have here in this problem is I have a pipe that I've drawn, so I have water flowing through the pipe, and I know that in that case I have a pressure drop, so I have a pressure at 1 and a pressure at 2. And so I know that the pressure at 1 is going to be greater than the pressure at 2. And what I want to do is I want to use a manometer to look at that pressure drop. So I want to know if I know some things about this manometer, can I determine that pressure drop? So what I know is I know the density of the water here, and in my manometer I have some oil which is at a higher density, so it sits on the bottom of this manometer. And I know the specific gravity of that oil, and if you remember, the density is equal to the rho of water times the specific gravity. That's what specific gravity means. Ooh, that's terrible S now. Okay, so I know what the density of the oil is, and I know the height difference here. So I know that the height here pushes the fluid down more, and I'm going to call that HA to this point A. And then I have a height here B, which is pushing down less to this height B. And what I want to do is, if I know those heights, I want to know, can I find what the pressure drop is? So let's go ahead and work that problem out. So to do that, I need to use my formula that we developed in class at the end of last time. What we said was that delta P is equal to minus rho G delta Z. All right? Pardon my flipping here, I just want to make sure. Okay? So what I need to do is I need to set up a series of equations for delta P and delta Z so that I can find the delta P between 1 and 2 that I needed to do. All right? And I'm going to need to use this concept which we said before, but I'm going to repeat it again. Since the pressure only varies with depth, the same connected static fluid at the same height has the same pressure. So same connected static fluid, static fluid at the same height, that has the same pressure. Okay? So I can use that principle. And I can use this principle right here, this equation, to find the pressure change. And that I'm going to do to relate 1 and 2. Okay? Notice that at 1 and 2, I'm moving. So this is, it's a connected fluid at the same height, but it's not static. So 1 and 2 can be different. Okay? But right here, underneath, it is static. Okay? Down here it's static rather, and so I can use that guy to go ahead and use my manometer. So the fluid's only moving up here. There might be a little bit of fluid moving around here, so I kind of want to, be far enough away from those regions where there's a little bit of inflow into my manometer. But other than that, I'm going to be pretty good. Okay, so I'm going to write down a series of equations to do this. So I'm going to pick these 2 points here. I'm going to pick PA and P1. So I'm going to say that PA minus P1 is equal to minus rho G. Okay, and then now I need to have ZA minus ZA minus Z1. So I need to make sure that if whatever I have here is different. So ZA is below Z1. So that means I'm going to have a minus rho. Oh, and I forgot something important now that I'm writing it. This here, this is the density of water. So this needs to be rho H2O right there, H2O. So rho H2O, I wrote it backwards, let me undo that. Rho H2O times G, okay, and then ZA minus Z1 is minus HA. Minus HA. So that gives me rho H2O GHA. Okay? And that makes sense. PA is going to equal P1 plus that. So that's, I'm just checking my minus signs there. The next one I want to do is on this other side. I'm going to have P2 and PB. So let me say PB minus P2 is going to equal minus rho H2O G ZB minus Z1, which will be minus rho H2O G minus HB, which equals rho H2O G HB. And again, PB is going to be higher than P2, and so that will give me PB is equal to P2 plus that. Okay, that seems right. So here's the last one. I somehow need to relate PA and PB, but I can use this principle right here. This principle right here, that the same connected static fluid at the same height has the same pressure. So I look here and I say, look, this A over here at the same height, A prime, okay, this is the same fluid at the same height, and it is static. So A and A prime have to have the same pressure, which means, because I can't vary in the x or y direction, I can only vary in the z direction, which means I can say that PB minus PA is equal to minus rho oil now, because this is oil here that's connecting these two pieces, G, and I have ZB minus ZA. Okay, ZB minus ZA is equal to, let's see, ZB is right here and ZA here, so that's going to be HA minus HB. So minus rho oil G, and this will be HA minus HB. Okay, and that's because HA is this whole distance and HB is that distance. So if I want to get the difference, I need to subtract HA minus HB. That's where that comes from. Okay, so now what do I have? I want to find delta P. That's what I want to find up here, this pipe flow, which is P2 minus P1. That's what I want to find. Well, now I have to use my expressions right here to find P2 minus P1. So I'm going to do that. I can solve for P2 here. P2, before I write that out, let me just solve for P2. P2 is equal to PB minus rho H2O GHB. And I'm going to solve for P1. P1 is equal to PA minus rho H2O GHA. And I have a relationship between PB and PA, but I'm going to use that in my solution here in a second. So I have P2 minus P1 is going to be PB, that was not my best P, PB minus rho H2O GHB, and then minus P1, so that will be minus PA plus rho H2O GHA. All right, and now I have PB minus PA, right? So I can separate that out. PB minus PA, okay, and then plus rho H2O G, and now I have an HA minus HB. Okay, now I'm going to take this piece, and I have it right here, which is minus rho oil G HA minus HB in parentheses plus rho H2O G HA minus HB. Okay, now this HA minus HB, I'm going to give it a name. I'm going to say just to make my life a little easier, sorry for the extra scrolling, I'm going to call H equals to HA minus HB. So that will go in right there, and that will go in, oops, not far enough, that will go in right over there. Okay, and I'm going to substitute that I know rho oil is equal to the specific gravity times rho H2O. I'm going to plug those two pieces in. So now I know that my pressure drop is equal to minus rho H2O times specific gravity times G times H plus rho H2O times G times H. So now I can pull out the common factors of rho, G, and H. And I'm going to have rho H2O times G times H. And this gives me a factor of 1. And this gives me a factor of minus the specific gravity. Okay, so now I think I have a solution, and I just need to plug in some numbers. So I have delta P is equal to rho H2O times G times H times 1 minus the specific gravity. Put a box around that. So now to solve for this, to find a number, rho H2O, if we scroll up, was 10 to the 3 kilograms per meter cubed. G is 9.8 meters per second squared. H, let me put a better 9 there, H is, I said, was HA minus HB, which is 10 minus 5. So that will be 10 minus 5 centimeters. And then the specific gravity was 1.2. So that's 1 minus specific gravity, 1.2. And I need to include a unit conversion here. So I need to put that there are 100 centimeters per 1 meter. And so I should get out in the end. Let's do the calculation right here. And open a little Python terminal. And we can do 10 to the 3 times 9.8 times 5 times 1 minus 1.2 divided by 100. And I get negative 98. So this is, negative 98. And what are my units? I have kilograms. Let's see, centimeters cancel. And I have, I'm going to have kilograms, meters squared per second squared divided by meters cubed. Okay, I know that a kilogram meter per second squared per meter squared is equal to Pascal. So this is pascals, minus 98 pascals. Okay, and so that is my pressure drop. Found the pressure drop. Okay, so that's the example I wanted to show you on manometers. That's all I got.